Cylindrical coordinates are generally really easy for students to understand. It's basically just something that you're very familiar with already, polar coordinates, and then you just stick a z on the end there, and you got cylindrical. It's pretty easy to deduce these formulas here if you're comfortable with polar, and sometimes you should remind yourself that this is where the x and y coordinates go. But what matters to you in calculus class is being able to calculate volumes and masses and charges in solids and surfaces sometimes that use cylindrical coordinates because people build things out of cylinders. So here's what you need. You need the volume differential. You can see down here I've drawn a very small box in polar coordinates. Here I actually had to draw a little piece of the polar grid, so you can see this change right here is the change in the radius, and then this change right here is proportional to the change in the angle, except that distance gets bigger the farther out you go, so you have to scale it up by a factor of r. Then the formula for the volume differential should look very familiar to you. Hopefully you can recognize this right here as being the area differential, and you'll recall from polar coordinates that the area differential is just r dr d theta. So that's basically just what happens right here. Spherical coordinates is different from cylindrical coordinates because it has two angles and one length, whereas cylindrical coordinates had two length coordinates and one angle coordinate. You pronounce this letter rho. There are two acceptable pronunciations of this. You can either say phi or phi, and then we're all familiar with theta. How do we define these coordinates rho and phi and theta? So imagine that you are only in the plane that contains the z-axis that makes an angle theta with the x-axis. That's this plane right here. And I've copied that plane here so we can see it a little bit more clearly. Now the definition is to make an angle between the point that we're trying to locate and the z-axis, and then phi is the angle down from the z-axis. Now be careful, this is very strange. Almost every other time that you've defined an angle, theta has always looked like an angle that opens up from something. And it does here open from the x-axis towards the y-axis. But phi, this is just the choice that we make. This is just because this is the useful way in applications to define phi. But I'll just warn you as math students, it's a bit weird. A lot of times students want to put the angle phi down here in the corner. Rho is the distance from the origin out to the location point. So that's basically like the radius of a sphere that contains the point that we're concerned with. Once you're in the plane that contains the z-axis and makes this angle theta with the x-axis, you're just one quick SOHCAHTOA away from switching back to rectangular coordinates. Since this region that we're looking at is a rectangle, I've just copied this variable r up onto the top. And then you can see here's our angle phi. So z is adjacent to phi, and rho is the hypotenuse of this triangle. So that means that the cosine of phi is z over rho. And you can go through a little talk if you want about sine as well. Then if I solve this for r, I would get r equals rho sine phi. And you can just take those and plug them in right here for r, and that will give you the change of coordinates to For the volume differential, we're imagining that way off in the distance, the origin has an angle that's made with these two pieces. And then how much down the angle goes, remember phi is actually opening in this direction, will give you the small change in angle. So right on the inside there is d phi. And then this whole distance out to the object is rho. So that means this length across this piece right here will be the distance out times the change in angle. Way off in the distance at the origin here, we extend out, and however far we go is rho. So that means this is the inner radius of the sphere, and this is the outer radius in the sphere. So this little chunk of the box changes by some small amount in the radius. So I'm calling that d rho. The length along the bottom side of this little curved box is actually the same as this length right here in cylindrical coordinates. So this distance is just r d theta, and then remember r and sine of phi and rho all have a relationship with each other, so I just substituted that value for r here, and I get rho sine phi d theta. Now when d phi, d rho, and d theta are all very small, this is approximately a little cube. Therefore, the volume of this little cube is just going to be the product of all of these differentials. So we get dv equals rho squared sine phi d rho d phi d theta.